All right. Good morning, everyone. Hope you had a good Thanksgiving.
I did, sir. Thank you.
Good. We've got 2 more weeks of class, and so we're going to try and pack so much stuff into those 2 weeks that you'll be really ready for the final when it comes around. But the good news is we don't have a project in this course, and so you don't have that hanging over your head, right? We do have 2 more homework assignments, though. Homework 7A, which is due on Thursday, and then homework 7B will be due next week. What we're going to do today is just to kind of hopefully refresh or cement the ideas of Chapter 7 in your mind. You know, it's maybe been a week since you thought much about fluid mechanics. We're going to do a critical thinking activity that in the past I had as a quiz. And so you can think of it as you're getting off easy because the first page of this, actually the first page of this and the first page of the second paper was a quiz in previous semesters, but this time you're going to receive this in more of a relaxed environment. So what I'd like you to do is see if you can write the energy equation from memory. And even if, oh yeah, put your notes away. So write the energy equation from memory, and if you can't quite get all the way there, see if your classmate or someone can help you out. And then go through some conceptual questions that are on here related to why the energy equation is written the way it is. Because remember, there are certain things that are on the right-hand side of the energy equation, certain things that are on the left-hand side of the energy equation, and why is it that they're in those spots? The left side and the right side are not interchangeable in the energy equation. So I'd like you to consider that for just a moment. So do the first problem, which is the front and back of the first page. And if you'd like, you can get started on problem 2, but I'm going to interject and we'll discuss the first page before I then turn you loose on the second problem. Okay, I've got the energy equation up on the screen there, as well as my short answer explaining what's different on the left versus what's different on the right. So take a look at what I've got and compare it to what you'd been thinking of. I'll give you a moment to soak that wisdom in. All right, so what I've just written on the whiteboard is that energy is in 3 places. Energy is in pressure, elevation, and velocity. So look at the energy equation. It's saying the pressure head and the velocity head and the elevation head. So those 3 things at location 1 plus the amount of energy that's added by a pump. Now what we're doing is we're applying this equation between 2 points. So we're saying the water is flowing from 1 towards 2. And this question, the equation is essentially answering the question, how much energy is at 2? So if someone said, how much energy is there here at 2, you'd say there is the energy at 1 plus however much energy is added by the pump that's in between them. And then the amount of energy at 2 is reduced by the energy that is lost due to pipe friction and local losses. So those are the 2 components of the head loss. And then the turbine also reduces how much energy is at 2. So think about this equation as a sentence. And it's saying the amount of energy at 2 is the amount of energy at 1 plus the energy added by the pump minus the energy that is lost due to friction and local losses and the amount of energy that's lost or extracted rather by the turbine. So it's basically telling you where the energy is in between 2 points, how it's added and where it's lost. So that's why things on the left are slightly different than things on the right. And then what are some of the key differences between this and the Bernoulli equation? Okay, yeah. That's maybe the most important thing is that Bernoulli equation didn't account for energy losses, and we are. What are some of, I thought you guys were going to shout Marshall just now when I said we are. You know? Got to be careful with how you use that phrase, but yeah. All right, so how else is it different? Okay, alpha, right, because now we're considering the velocity at a certain, rather than a certain location like Bernoulli's equation did, we're using it across the cross-section, and so that's why this V bar, it's saying the average cross-sectional velocity. Okay, so any questions about the equation or the differences between the left side and the right side? Okay, is it a pump or a turbine? How do we know it's a pump? There's an energy loss and elevation difference. The water can't flow uphill unless something is adding more energy. So it's a pump. Since the flow is going in the direction indicated by the arrow, energy has to be added. To get water to go from 200 up to 300, you have to be adding at least 30 meters of pump head. And it's not going to go, I mean, if you're only adding 30, it's not going to run. The pump would just kind of be like locked. But if you add 31 meters of pump head, the water is going to flow really slowly. You add 40 meters of pump head, then maybe the water will go a little bit faster because you've got more energy to spend on overcoming the effects of friction losses. Okay, so on the back side, let's see, what is the meaning of R to D? Now I forgot to tell you, there's some data on the last side of the paper. So let me pause for a moment and let you consider all of that data. And if you don't yet know what R to D might be, think about that table of data on the last page. Okay, so on the sketch, it says that we've got an R to D of 1. And what that means is it's the radius of curvature relative to the diameter of the pipe. So that's a relatively abrupt turn. It means that, you know, if you have a 50 centimeter diameter pipe, that the radius of curvature is 50 centimeters. And so you'll notice here that we've got different K values depending on how smooth that bend is. And so for one that's as abrupt as what we're seeing, the K value of 0.35, the way that that K value is used is you multiply the K value by the velocity head at that location, and it tells you how much energy is lost due to that fitting. And so if we have this 90-degree smooth bend, and we know the velocity through that bend, we can calculate the velocity head, and then the number of meters of energy loss will be v squared divided by 2g multiplied by the k that we get from this table. And so there'd be less energy loss if the bend wasn't as abrupt. So this 2 means that the radius is 2 times the diameter. And so that means rather than having the pipe change so quickly, this is maybe what r to d of 1 would look like. If it was instead it was 2, then it's going to be a more gradual transition. Okay, so now we've got here r to d of greater than 1. Why is, according to this model, it's saying you're going to have less energy loss if the transition is more like that instead of like abrupt? Any guess on why we can expect there to be a lower k value and therefore less energy loss? The change in direction is more gradual. It's still changing, you know, from x to y, so you end up with the same endpoint, but we're not inducing turbulence as rapidly. And this energy loss is because of an abrupt change in direction is going to disturb the flow patterns. It's going to introduce more random movement inside of the pipe. And so there are energy losses because of that disturbance. And so we're trying in all of these fittings to consider how much turbulence is induced by the fitting in question. And so what it tells us is there are certain types of valves that induce a lot of turbulence. Like consider a globe valve. A globe valve has a big K value, whereas a gate valve has a low K value. And a gate valve is essentially, it's just a pipe that a little, like a door can be lowered down. It's kind of like, you know, a castle door that just goes straight down and can be lifted straight up. So when it's up and it's open, the gate valve doesn't cause much disturbance because it's just, you know, there was a pipe where something impeded the flow, and so it's closed. Of course, it's not letting any flow through there. But when it's open, there's less disturbance than compared to if there's like this ball valve that just has like a small hole through the center. And so a ball valve, sometimes they turn it so that the hole isn't in the flow direction, and sometimes they turn it in the direction of flow. And so all of the water has to squeeze through this little opening in a ball valve. So there's going to be a lot of energy loss in a globe valve. So that's what all of these are trying to assess, is the amount of turbulence that's induced. Yes? I'm glad you asked that. Yeah, so he noticed the K value starts increasing. So it seems like the sweet spot, if you're trying to minimize energy loss, the sweet spot is an R to D of 4, because beyond that, it's getting higher. What it means is now you're getting excess length. And so they're kind of building into that the friction losses, because you're making a transition longer than it needs to be. I'm glad you noticed that. So these K values are cumulative. And as long as the velocity is the same at every point, you can just add them up. That's why in the formula we're saying the sum of the K values. Because if you have a pipe that has, let's say it's got 2 bends and a valve, you know, if the water is going and then it changes direction and it changes direction again, all you need to do is find the K values. You know, here's maybe 0.35. Here would be maybe 0.20. Maybe we throw in a gate valve here that's not closed. And so here's, what's the gate valve? 0.2, 0.2. You just add them all up, you know, and then the sum of the K the sum of the K's you multiply by the velocity, as long as the velocity is the same at all of those points. You know, if the pipe changed diameter, then you need to apply the velocity at the point in question. So if we had choked down this pipe and now it's like narrower, then we couldn't use the same velocity head for all of them. We'd have to calculate the local losses here and then a different velocity head for all the remaining K values. Does everybody get what I'm saying there? That you can only add them all up if the velocity is the same at each of the locations that are being included in that sum. Okay, so besides the elbow, what are the two other locations where localized energy losses could occur? So we're not talking about pipe friction. We're talking about localized energy losses. And I'll give you a hint. One of them is not the pump. The amount of head that's added by the pump takes into account any kind of internal losses that occur due to turbulence on a localized basis. So we only know the net head addition from the pump.
Is there a pressure head loss?
The pump adds pressure head. That's how it adds energy. Yeah. So there's the elbow where there's a local loss. The other two spots are at the entrance where the pipe goes from a tank into the pipe. And if we go down here to the table, that is this. So the R to D for where you have a really large diameter tank, so essentially it's a pipe entrance here where it's an abrupt edge. So the R that they're talking about here is the radius of curvature around the pipe entrance. And so if it's just a pipe projecting up to the wall of the tank, then the R to D is 0. So the K sub E is 0.5. So that's one of the spots where there's going to be a local loss. There's an entrance loss associated with the water going into the pipe. And so which velocity do you use? Use the velocity in the pipe, because inside the tank there's no velocity. So use the velocity in the pipe when the water is going in there. And then the other loss is at the discharge. And so if we go back down to the table, then we see that that is kind of like a pipe expansion. So we have in this table, if you connect two pipes of different diameter, then the water is going to be disturbed by that. And the general trend is the smaller the change in diameter, the less the disturbance is. And so if the ratio of the two diameters is close to 1, that means that there isn't much of a change. And so, for example, they're also taking into account whether it's an abrupt transition, like if the angle is 180 degrees, then what that means is that the two pipes are coming together like this. And so 180 degree transition is like that, whereas there would be less energy losses if we make it a gradual transition. So that the angle that they're referring to here is related to the taper between the two diameters. But the extreme example is that the diameter 2 is so big that the ratio is 0. And in that case, you lose all of the velocity head. So 1.0 means that as the water flows through the pipe, it's got some velocity head, right? So some of the energy, if the question is where is the energy, it's in 3 places: velocity, elevation, and pressure. So some of the energy is existing as velocity head, and then it discharges into the tank. That energy is just instantaneously lost as the water goes from the pipe into the tank. And we'll talk more about how to visualize that and why it occurs, but that's the third spot where there's a local loss in this system. Okay, energy is also lost as water flows through the pipe. So I asked you to write 3 factors that you think could influence the rate of energy loss through the pipe. If you didn't already write something down, I'm going to pause for a moment so you can think about that. What are the 3 factors that can influence the rate of energy loss due to pipe friction? Okay, water loses energy when it flows through the pipe. You know, that's the pipe friction. So I asked you to think of 3 factors that influence the rate of energy loss through the pipe. So sometimes you're losing pressure really fast as the water flows through the pipe. Sometimes you're losing pressure really slowly. And you've observed that in the lab. Remember the differential pressure gauge that you plugged into the pipe rack? Sometimes it was saying a big number. That was a lot of energy loss due to pipe friction. And sometimes it was saying a small number. So do you remember which pipes was it that you plugged in and you saw a big number? It was the small pipes. Exactly right. So what was it about those small pipes that made the rate of energy loss? When I say rate, that means change in pressure per length. That's the rate, is some amount of energy loss over some distance. And so that was a rate because each of those taps were a meter apart. So why is the small diameter pipes you're having such a high rate of energy loss? Smaller cross-sectional area. And what does that do to the velocity when you're trying to force a lot of flow through a smaller cross-sectional area? It increases the velocity because we know V is Q divided by A. So if you have small a, then you have big V, right? So here is the equation. This is the Darcy-Weisbach equation. It tells us the rate of loss. And so for a 1 meter length, you know, if the length is constant, then a high velocity will give you a high friction loss. And look, diameter is down in the denominator. And so that's only going to amplify the effect, because if you have a small diameter, so now you've got a small number in the denominator and a bigger velocity. So small pipes lose energy much more quickly than large pipes. And that's why if you're designing a water network in a city, you have to ask yourself, how big should the pipes be? And it's all about managing pressure. You'll do this in the project that we have next semester in hydraulic engineering. You're going to be asking yourself, do they have enough pressure at this part of the city? You know, because you don't want to give them too much pressure because it just costs you money to make the pipes big. So you're going to give them just enough pressure so that people don't complain, like the minimum amount of pressure. Because it's kind of like, it's the currency that you've got to spend, is the energy that's being delivered at every point in the system. Okay, so velocity, diameter. Anybody think of other factors that can influence the rate of energy loss through the pipe? Pipe material. Yes, some pipes are made out of a really smooth material, like a drawn glass is going to have a low friction factor. Some pipes are made out of a more coarse material, like cast iron, which has a much higher friction factor. And there are some other factors as well, like the temperature of the water can have an effect because that influences the Reynolds number. So we'll talk a lot more about that next semester. Okay, now it's time for crunching some numbers. Calculate the flow rate for this system. I've put some details in. I've given you the elevations. We had those elevations before, but now what we've got is a friction factor, a pipe length, pipe diameter, but we don't have the flow rate. That's what I'm asking you to calculate, is find Q. So to find Q, you're first going to have to solve V. And so remember, there are 3 places where there are local losses. There's a local loss at the entrance, there's a local loss at this bend, and then there's a local loss at the exit of the pipe. So you add up those 3 Ks, and it'll be multiplied by the unknown velocity. And then you substitute in all the factors that are known for the pipe, the friction factor, the length, the diameter. Put all of that into the H sub F equation, and you're going to substitute that information to solve for the unknown V. So remember, here's the energy equation up here. Ooh, I went much too far. Here's the energy equation. The water's flowing from 1 towards 2. What do we choose as 1 and what do we choose as 2? Well, I'll let you discuss that with your classmates. I'd like you to work and try and solve what is the flow rate in that system, what's the flow rate through the pipe? So somebody who's already finished, remind me, why did we pick location 1 to be the reservoir on the left? Good, right. So the flow direction is 1 is upstream, 2 is downstream. Now the energy equation is valid for any 2 points in the system. We could have applied it here in the pipe and there in the pipe. But you have to think, where do you know things? Because you want to apply the equation so that there's only one unknown. And if you right off the bat are just picking random points in the pipe to solve for, you're going to have too many unknowns. But if we use the reservoir water elevation, then we know the water elevation is Z. We know that pressure is 0 because it's in contact with the atmosphere and we're working on a gauge basis, so pressure is 0. We know that in a big tank like that, the velocity at the water at the surface is effectively 0, near enough that we can just consider it as 0. So it's customary to pick your location strategically, maybe where you have a pressure measurement and where you know the elevation and you know the flow velocity. And so that's why we pick 1 and 2, the locations that we did. You'll notice that I've identified the K value at the entrance of 0.5 because that's an extreme example of taking a pipe contraction to the extreme example of upstream. The pipe is infinitely large diameter going down into a pipe of some non-infinite diameter. So the extreme K value for that case with a square edge transition is 0.5. The exit loss of 1, and then an elbow with an R to D ratio of 1 so that we get the K value there. So you'll notice what I've canceled out and what remains. The pump is adding 40 meters of head, and so it's 10 meters of head that can go towards overcoming losses, and 30 meters of head is overcoming the elevation difference. So that's how that 40 meters of head is being spent in the system. 30 meters to increase the potential energy, and 10 meters to overcome local losses and pipe friction. And so we've got both in this system. We've got the pipe friction, which is F L V squared divided by D2G. That's the Darcy-Weisbach friction equation, which I know some of you have already seen before because it was included in your reports for the fluids lab. And then here's our local losses. 1.85 is the sum of the K's. And what V is it talking about there? This isn't V1. This isn't V2. This is the V in the pipe. And that's what you always use for local losses and the friction losses. It's talking about the velocity where the energy loss is occurring. And the energy loss occurs not at 1 and not at 2, but between them. That's where the loss is occurring. And so it's the velocity inside the pipe that we're solving for. And the velocity should be in the around 2.233, maybe a little different depending on your round-off situation. But our flow rate should be about 0.28 cubic meters per second. And I saw that on several papers as I was walking around. So that's the energy equation. Any questions on the example? Okay, we've got 20 minutes left to go through all of these slides. I think there's a couple of examples that I have, and I also have some key ideas on the homework. So if I don't stop by 12:10, start waving your arms so that I'll have enough time to tell you those key ideas, all right? So we've got 15 minutes to go through some of this other stuff before I give you the key ideas. All right. So let's consider another situation. You probably all calculated out, so I'll do this one. What if we have a situation where two tanks are connected together and we have a pressure measurement that is taken 545 meters apart, and there's a slope in the pipe, and so that means that the pressure measurement is partly because of the elevation difference, and it's partly because of friction losses. So that measurement of the pressure difference that we have isn't all due to pipe friction. You know, like in a horizontal pipe, sometimes in problems like this I tell you the pipe is horizontal, and what that allows you to do with the pressure measurement is if the pipe is horizontal and there's a pressure difference, the only cause of the pressure difference is friction losses. But here there's two sources of the pressure difference. So we want to find out what is the head loss here. So we're solving the energy equation, which is shown at the bottom of the screen, and we can apply it at the 2 points where we have information. So what do we know at, in the good old days, I used to be able to write on the screen because it was a projection onto a whiteboard, but now they get mad if I write on the screen. You won't say anything? Yeah. You know, I wouldn't take away points, but somebody would trace it back to me. They'd know. They'd know it was me. All right, so we've got 2 points, and so you'll see what I'm saying is the point 1 and 2 are going to be these locations where we've got the differential pressure measurement. So the upstream and the downstream. So 1 is upstream, the water's flowing from west towards the east, and the length 545 meters. Okay, so what we're going to do with this slope that's given is that's going to define the z values of 1 and 2. So let's have it be so that let z2 is 0, and we want to find out what's the elevation of location 1. So how do you do that? Exactly right. Yeah, so he said we've got a slope percentage, so z1 is going to be the slope percentage of 0.03, because it's 3% slope, and what that percentage is it's how much rise there is for how much run. So 3 feet of elevation gain for every 100 feet of horizontal length. And we have 545 meters of horizontal length, and so then that means that the elevation at location 1 will be 16.35 meters. All right? Okay, now in the sketch there's no pump, and so H sub P is 0. There's no turbine, so H sub T is 0. So what we have for the energy equation is P1 divided by gamma. We've canceled out the velocity head term because V1 equals V2 because the diameter isn't changing in the pipe. So if the two velocities are the same, then that means V1 squared divided by 2g is equal to V2 squared divided by 2g. So if it's the same on the left and on the right, then that means the velocity head term doesn't need to be included. So it's not that the velocity is 0. When I'm canceling out the velocity head term, it's not because the velocity is 0. It's just that the velocity at 1 and the velocity at 2 are the same because the pipe diameter is constant. Okay, so I've got the pressure head, the elevation head at 1 is equal to the pressure head at 2. I let Z2 be equal to 0, so I'm not going to include that. But then there is the head losses, H sub L. Okay, so we can rearrange to solve for head losses. Head loss is P1 minus P2 divided by gamma plus Z1. So I just moved the pressure head at 2 term over to the left side, and they have that common gamma as the denominator. So P1 minus P2 divided by gamma plus Z1 is equal to the head loss. All right, so what pressure was measured? What we know is a measured pressure difference was 86 kilonewtons per cubic per square meter. That's the units of pressure. And then the unit weight of water is 9.81 kilonewtons per cubic meter. Now I could have converted that to newtons per square meter and this to newtons per cubic meter, but if it's in kilonewtons in both the numerator and the denominator, then I don't need to switch it necessarily. And then the elevation difference of 16.35 meters means that I can now solve for the head loss, and H sub L is 25.12 meters. All right, so the pressure changed. We observed the pressure change was 86 kilopascals. Some of that pressure change was due to the elevation difference, and some of the pressure change was due to head loss. Any questions about that? All right. Turn the screen back on here. Remember that we previously had a slide that explained the difference between energy, work, and power. And energy and work have the same basic units, units of joules, but then power is when there's a time dependency. And we're talking about how much work is being done per time, or the amount of energy consumption per time. So watts are joules being used per second. So in fluid mechanics, the power equation is you would multiply either the turbine head or the pump head by gamma and Q. And then it would tell you how much power is either being consumed or how much is being generated. So let's do an example to illustrate efficiency and how that comes into a play. This is an elevated reservoir where water is flowing down through this penstock, which is basically just a large diameter pipe. And because of the elevation change, it's spinning the turbine. There's going to be a lot of pressure inside the penstock, and what's happening is that the pressure is being extracted by the turbine, turned into mechanical movement, which is then turned into electricity by the spinning generator. Just to illustrate these calculations, let's consider that at the upper reservoir we know the elevation is 1324.4 meters. We have an elevation for the lower reservoir, and we've calculated the head loss through this pipe, 5.4 meters of head loss, and we know the diameter of the penstock and the average flow velocity. So here's the power equation. This power equation that's shown assumes that there is no losses due to the inefficiency of the turbine, in this case, this being a turbine, we'd assume that there's 100% conversion between the energy that's available to be extracted from the system and the electricity that's generated. But typically, there will be an efficiency factor both for the turbine and then also for the generator. And so we need to combine those two together. So let's calculate how much electricity should be generated if the turbine's 100% efficient, or what if it's not 100% efficient and energy is being lost. So 70% efficient. So for the first case of 100% efficiency, what we need to solve for is the pump head. We're solving energy equation for H sub P. And so we start by just writing the full version of the energy equation. So P1 divided by gamma plus V1 squared divided by 2G plus Z1 plus H sub P is equal to P1 divided by P2 divided by gamma plus V2 squared divided by 2G plus Z2 plus HL plus HT. All right. So what we are using as location 1 is the upper reservoir, and location 2 is the lower reservoir. All right, so there's going to be no pressure at either location because we're just talking about it's open to the atmosphere. There's going to be no velocity at either location because it's a tank or a big body of water where the movement of the water is negligible. There's not a pump, so we're canceling out the pump head term. So what we're solving for here is H sub T. So that's the unknown. So H sub T is going to be Z1 minus Z2 minus the head losses, H sub L. Okay, so any questions so far? This is basically just how much energy can be extracted by that turbine. So the amount of energy that can be extracted is the elevation difference, but you can't extract the energy that was lost due to friction losses, right? So if we put in the elevation difference, I keep switching the screen off so that the solution can be on the video. All right. So Z1 is 1324.4 meters. The Z2, so we're subtracting 1191.9 meters, and we're also subtracting the losses. The losses are 5.4 meters. So the H sub T, this is how much energy can be extracted by the turbine. It's 127.1 meters. Okay, now the power equation, P is the flow rate times Q times H sub T. We have to know the flow rate to be able to put it into the power equation. And so previously given in the problem statement is both the diameter of the pipe and the flow velocity. And so if the diameter is 1.5 meters, then the cross-sectional area is pi d squared divided by 4. And so the cross-sectional area of the pipe is 1.7671 meters squared. So Q is the area, 1.7671 meters squared, multiplied by the velocity, and we were told in the problem statement the velocity is 2.4 meters per second. So the flow rate is 4.24 cubic meters per second. So that's Q. And so what can we put now into the power equation? We can put the flow rate, 4.24 cubic meters per second, we can put the unit weight of 9810 newtons per meter cubed, and then the turbine head. This is how much head can be extracted by the turbine, 127.1 meters. And multiply all that together, we're going to get that it's 5.29 times 10 to the 6th watts. So that's 5 megawatts. You sometimes hear those terms used for like wind turbines and hydropower plants. So 5 megawatts. So what happens if the flow rate goes down? How much electricity, the amount of electricity that's available? If the flow rate decreases, then you can't generate as much electricity. So that's one of the problems when there's a drought, like out in the west where they have these long stretches between rainfall. They have a lot of dams, and many of them are hydropower dams out west. And when they have really dry conditions, they can't send as much water through the penstock because they're trying to conserve it. And when you decrease the flow rate, then you're decreasing the amount of power that can be generated. Likewise, one of the problems they have out west is that when the reservoirs are low, the water elevation is lower, and so then that reduces the elevation difference that's available to increase the H sub t. So if you've got the double whammy of, your reservoir elevation is low and you have just a trickle of water going through the discharge, then you essentially you lose your ability to generate power. Now this problem said, if you have 100% efficiency, this is how much can be generated. So this is for 100% efficiency. That's assuming that all of the energy of the moving water coming in contact with the blades of the generator, it's perfectly transferred into electricity. But what if it's 70% efficient? Let's say there's a little bit of losses due to the conversion from the water's movement into the movement of the shaft on the generator, and then there's additional losses with the moving shaft to the electricity that's being produced by the generator. So what if it's 70% efficient instead of 100% efficient? Is this number going to be higher or lower if the system is only 70% efficient instead of 100% efficient? It's going to be lower. You're going to have less electricity going out over the power lines if it's not fully efficient. So should we multiply or divide by 0.7? We multiply, right. So the power at 70% efficiency is going to be 0.7 times 5.29 times 10 to the 6th watts. And so that is going to be 3.7 times 10 to the 6th. So 3.70 times 10 to the 6th watts. So if it's a turbine, you multiply by the efficiency factor. But if it's a pump and you're applying efficiency, you have to divide by the efficiency factor. We'll do an example that proves that to you, but the idea is that, as it says here on the screen, if you have a pump, you divide by the power equation efficiency factor because you're going to have to add more electrical energy into the system to do the work that you want done because of the inefficiency. But if it's a turbine, you were supposed to wave your arms. Okay, we've got 2 minutes for me to give you these key ideas. All right, so in problem 25, it asks you to find the discharge in the pipe and the pressure at B. So what you do is you find the velocity at the outlet. So you're applying the energy equation between the water surface and the nozzle. So the energy equation at location 1 and location 2. And I know you're excited to start calculating friction losses, but here they tell you to neglect the head loss in this problem. And that's an important point, is that the head losses are neglected. So You find the flow rate after you've solved for V2, and then the pressure at B can be calculated by solving the energy equation another time between location 2 and location 1, where the only unknown at location 1 then will be the pressure. So the emphasis I want to give you for this problem is to neglect the head losses. We've got 1 minute. On this problem, it's a similar situation. They ask you to find the pressure head at location 2. And we've got all this given information about the elevations, the diameter of the nozzle, the diameter of the pipe. So when they ask for the pressure head, what they're saying is solve for P divided by gamma. So they give you the flow rate, and you know the diameters in these pipes, so that tells you you can find the velocity in the pipe. And since the elevations are known, that takes the elevation term of the energy equation into account. What you have to do is you have to apply at the nozzle to be able to find the pressure at 2. And so the unknown, even though they've labeled this as location 2, this is going to be an upstream location. So this will be in the energy equation location 1, and location 2 will be at the nozzle, because that's where you know lots of stuff. You know the water pressure just outside that nozzle. So you're going to apply the energy equation from the jet that's just outside the nozzle down here to location 2. All right, one last tip on this problem is that the maximum allowable discharge before cavitation, the cavitation is going to occur here in this throat, because that's where the velocity will be the highest and therefore the pressure will be the lowest. So just before cavitation, what you're essentially doing is you're saying that the water pressure is equal to the vapor pressure. So you go to the back of the book, you look up what is the vapor pressure for 20 degrees Celsius water, and you set the pressure at that location equal to the vapor pressure, and then you solve for what flow rate, therefore which velocity, is going to make it so that you have that pressure at the throat. So these key ideas are, I think, in your notes, and they're in the printed notes. You've also got the video recording, so let me know if you have any questions as you work on that homework assignment. I kept you 1 minute long, so I'm going to give you 1 minute off on Thursday. So it's going to be ultimate relaxation. I'll see you then.